What you're looking at is not a video, it's a real-time, interactive water ripple effect coded 100% in Java. Click anywhere, and the ripples spread just like in real water. In this tutorial, I'm going to show you step by step how to build this effect from scratch, and you'll learn how the ripple simulation works under the hood. Now, let's add a brand new JFrame to hold our animation. We'll call it Ripple Frame. Once the frame is created, make sure to resize it to a comfortable dimension, like 800 by 600 pixels. Finally, let's give it a nice, descriptive title so our users know exactly what this is. We'll call it Liquid Ripple Effect. Next, from the palette window in NetBeans, drag and drop a JPanel right into our new frame. This panel will be the canvas for our ripple animation. Resize it so it perfectly matches the size of the JFrame, covering the entire area. Then, give it a clear name so we can reference it easily in our code. We'll call it Ripple Panel. Now, choose a suitable image for your water ripple effect. Move this image into your project's source folder so it gets packaged with the compiled files. Next, let's create a new Java class called Ripple Panel. We start with the standard Java imports for graphics, event handling, image processing, and swing components, everything we need to draw, animate, and interact with our ripple effect. First, we import the core Java AWT packages for drawing and colors, the event package for handling mouse input, the image package for working with pixels and buffers, and swing for building our user interface. Here, we define Ripple Panel as a subclass of JPanel. By extending JPanel, here, we declare the main variables for our ripple simulation. Base image is the picture we'll distort to create the water effect. Ripple Map 1 and Ripple Map 2 are two-dimensional arrays that store the water surface height at each pixel. We'll swap them each frame to animate the waves. Width and height store the image dimensions so our loops know their boundaries, and running is a simple flag to control the animation thread. In the constructor for Ripple Panel and two integer parameters panel width and panel height. First, we set the preferred size of our panel based on the values passed into the constructor, and we make it opaque so that our custom graphics will be visible. Next, we try to load a background image called water from our resources. If it loads successfully, we resize it to match the exact size of our panel. Next, let's take a look at the resize image method. This is the utility that makes sure our background image always matches the panel size perfectly. First, we take the original image and call getScaledInstance method, passing in the target width and height. We also specify scale_smooth. This tells Java to use a high-quality interpolation method so the resized image looks clean without jagged edges. Then, we create a brand new buffered image with the exact target dimensions, using the type integer RGB format. This matches the format we'll use in our ripple calculations later, which helps keep performance consistent. Next, we get a graphics 2D object from our new buffered image. This acts like a paintbrush for drawing onto the image in memory. We then draw the scaled version of the original image right onto this new buffer, starting from the top left corner at position 00. Finally, we dispose of the graphics context to free up system resources, and return the fully resized image. The result? Our background image will always be perfectly sized to fill the panel, whether the window is 800 by 600, full screen, or anything in between, and it will look sharp and professional every time. Now that we've loaded our water texture into base image, we immediately pass it through our resize image method. This ensures the image perfectly matches the panel's width and height, in this case, panel width and panel height. If loading the water image fails, we fall back to creating our own background from scratch. First, we create a brand new buffered image with the same width and height as our panel, using the type integer RGB format. This gives us a blank canvas to work on. Next, we grab a graphics 2D object from this image, which lets us draw shapes and colors directly onto it. We then set the paint to a gradient paint, starting with cyan at the top left corner and fading smoothly into blue at the bottom right. Using fill rect method, we paint the entire rectangle so the whole panel is covered with our gradient. Finally, we call dispose to release the graphics resources, since we're done drawing. This way, even if our texture file is missing, the ripple effect will still have a colorful, visually appealing background to work on. Next, we grab the dimensions of our background image, its width and height in pixels, and store them in variables. These values are important because our ripple simulation works directly at the pixel level, so we need to know exactly how many horizontal and vertical points we'll be working with. Then, we create two two-dimensional integer arrays, ripple map 1 and ripple map 2, each the same size as our image. Think of these arrays as two layers of water height data, one for the current state of the ripples, and one for the next frame. As the simulation runs, we'll constantly swap and update these maps to create the illusion of moving waves. Let's break down the method that creates each ripple, disturb, which takes the click position X and Y. We start with a radius set to 10 pixels. Think of this as the size of the splash when a drop hits the water. A larger radius creates a broader initial wave, a smaller radius gives you a tighter, sharper ripple. Next, we loop over a square region centered on the click, from minus radius to plus radius, both horizontally and vertically. That means we're scanning a compact neighborhood around the cursor to decide which pixels should be affected. Inside those loops, we compute distance. This is the squared distance from the center. Using the squared value as intentional, we avoid the slow square root operation and still get a perfect circle check. We then test if distance less than squared radius. If that's true, the current point falls inside the splash circle. Everything outside the circle is ignored, so the ripple has a clean, round shape. Now we convert from local offsets to absolute coordinates. Before we write anything, we clamp with a quick boundary check. Px and Py must fall within the image width and height. This prevents out-of-bounds access at the edges. This adds energy into the height map at each pixel inside the circle. You can imagine we're pushing the surface upward by a fixed amount. The exact value, here, 512, controls the strength of the initial displacement. Higher values make bigger waves, lower values make a softer tap. In short, disturb method is your virtual fingertip touching the water, precise, fast, and easy to tune. Next, we give our ripple effect some interactivity. We attach a mouse listener to the panel, and specifically override the mouse clicked method. Whenever the user clicks anywhere on the panel, this event captures the exact X and Y coordinates of the mouse. We then pass those coordinates into our disturb method, the same one we just discussed, which instantly triggers a splash effect at that position. This is what transforms our static image into an interactive water surface you can click and play with. Now we're moving on to the most important part of the ripple simulation, the ripple step method. You can think of this as the heartbeat of our virtual water. Every single frame, this method runs to update the position and intensity of each ripple. The very first line here might look a little strange, but it's actually a clever trick. We're swapping the roles of our two ripple maps, ripple map 1 and ripple map 2. One map holds the current frame's data, while the other stores the next frame. Swapping them avoids having to create new arrays every time, which keeps the animation smooth and efficient. Next, we loop through the image, pixel by pixel, starting at 1 and stopping just before the edges. That's because the border pixels don't have all 4 neighbors, and trying to access outside the bounds would cause an error. Inside the loop, we calculate the new height value for each pixel. Imagine dropping a pebble into a pond. The water at one point moves because of the water next to it. Here, we take the height values from the 4 neighbors, left, right, top, and bottom, add them together, and then divide by 2 using a bitwise shift. Then, we subtract the old value from the other map. This subtraction is what makes the waves move outward instead of just blending together into a flat surface. Finally, we apply a damping effect. In simple terms, we're reducing the height value a little bit each frame so the ripples naturally fade away, just like in real life. Without damping, the waves would keep bouncing back and forth forever, which would look pretty unrealistic. And that's the magic. In just a few lines, we've recreated how water moves, spreads, and slowly returns to calm. This method runs again and again in our animation loop, giving life to the whole effect. Alright, now let's look at one of the most important parts of our program, the animation loop. This section starts by creating a new thread. Why a new thread? In Swing, the user interface runs on something called the event dispatch thread. If we put long-running code there, the interface would freeze. By creating our own separate thread, we keep the animation running smoothly without locking up the rest of the UI. Inside this thread, we've got a while loop. This is our heartbeat. As long as the running flag stays true, this loop will keep executing over and over. The first thing it does each cycle is call ripple step method. After updating the ripple data, we call repaint method. Thread class sleep method passed the value 16 milliseconds. This works out to roughly 60 frames per second, which is the same refresh rate as most monitors. Now let's break down the paint component method. This is where everything comes together visually. In Java Swing, paint component is the method responsible for drawing our panel's contents on the screen. Every time we call repaint method, Swing eventually calls this method, giving us a fresh graphics object to draw on. The very first thing we do here is call superpaint component method. This is important because it ensures that the panel gets cleared and any default background painting happens before we start drawing our custom graphics. Without this line, you might end up with leftover artifacts from previous frames. Next, we create a new buffered image called frame. Think of this as our temporary canvas for the current frame of animation. We give it the same width and height as our base image, and we store its pixels in an integer array called pixels. Each element in this array represents a single pixel's color in RGB format. We tap straight into the picture's pixels. That means we can change the colors directly instead of asking Java to move the whole image around, much faster for animation. Then we walk across the picture pixel by pixel. We'll leave a tiny border alone so we don't read outside the image. At each spot, we figure out two tiny nudges, left/right and up/down, based on how the water surface rises or dips around that point. Those nudges tell us which nearby pixel to show, creating the wavy look. Once we figure out where to grab the pixel from, stored as NX and NY, we make sure they're within bounds so we don't crash. Then, we copy that pixel color from the base image into our frame's pixel array. Over time, as the ripple maps change, these shifts create the illusion of water moving and distorting the background. These offsets tell us how to shift the pixel's position to simulate the bending of light through water. Imagine looking into a swimming pool, the tiles under the surface look wavy and displaced. That's exactly what we're mimicking here by sampling the color from a slightly shifted location in the base image. This process happens roughly 60 times per second, creating smooth, continuous water movement. The combination of the height map from ripple step and the pixel displacement here in Paint component is what gives our simulation that realistic liquid feel. After processing every pixel, we finally draw our frame image onto the panel at position 0, 0. And just like that, the new rippled frame appears on the screen. Now we need to make sure our ripple panel has the correct size when it's added to the form. In NetBeans, right-click on the form's constructor code area and choose Customize Code. Here, we'll replace the default panel creation with our custom one. Specifically, we write ripple panel equal new ripple panel 800, 600. This tells Java to create our ripple panel with a width of 800 pixels and a height of 600 pixels. This initializes our custom panel with a size of 800 by 600 pixels, ready to render the water ripple effect. Next, we add it to the frame's content pane with getContentPane method. This step actually places our animation panel into the window so it's visible. Finally, we call pack method which tells Java to automatically resize the window so it fits the panel perfectly, with no extra empty space. Alright, our JFrame is ready and the ripple effect is built in. You can now run the program and watch your water animation in action. If you want a more realistic look, use a background image of your choice. Or, for a clean and modern style, keep the gradient color background. That's it, you've created an interactive water ripple effect in Java Swing. Thanks for watching, and if you found this helpful, please like the video, subscribe to the channel, and hit the bell icon so you don't miss more awesome Java tutorials.